Uh, I will specify a formal definition of the relation of binary relation in a moment, but let me talk a little bit intuitively about what relations are, and I want to also describe them and contrast them with two other types of objects that you all probably discussed more in your previous math education, and to see how are they similar, how they are different. Let's first discuss what's a binary operation. Binary operation is like addition, subtraction, and all these operations that you study throughout mathematics. So what would that be? That's like a machine that has two feeders and one output. Okay? And then what? You feed two numbers, 7 and 3, and you get their sum, and that's 10. So that's called operation. So look at the type of the object. You usually get objects from a structure, and very often you get objects from the same structure or some other type of objects. So objects in, objects out. Do you see that? So you add up two numbers, you get a number. What about function? Again, you specify, and then what? You specify here when you have function of one variable, let's say in calculus 1, then let's say f of x equals x squared, and you feed the number 5, you get 25. Again, you feed objects, you get objects, and you insist when you feed the same object, you get the same result. Is that clear? What about binary relation? Generally, I always think of it this way. You feed two objects, and the output is yes or no, true or false. And that's a huge difference. So they sound, format-wise, they sound similar like operations, but actually the meaning is dramatically different. So what would that be? So for example, for two, how do I define to say yes or no? It's up to you. Different ways to define yes or no are different types of relation. So example, let's say I want less than. So if I want, is that a relation or operation? When you feed in 3 and 7, you're not going to get a number. You're going to get true or false. Do you agree? So 3 less than 7, what's your output? True. And then if you put 7 left, 3 on the right, you will get false and so on. Is that clear? So output here is true, false. And that's why the result of a relation could be part of a predicate formula. You know, so on they are related and the others are related and so on and so on. So that's the idea. What, by the way, in this course, we'll mostly define binary relation. Does anything prevent us from ternary, the relations when you have feed 3 objects? So just a side comment. Ternary relation, let's say this, x plus y z equals 10. So x, y, and z are related. We'll say r of x, y, z, if and only if x plus y plus z equals 10. So if I feed 3, 5, 7, what will be your answer, yes or no?
False.
False. And then how many inputs am I feeding? 3 inputs, so that would be ternary. Relations could be of any length. Could a relation be of length 1? Yes, usually we call them predicates or properties. So for example, I can say the following. E of x is equivalent, there exists k from z such that x equals 2k. Does this look familiar, this property? This is property of being what? Even. And then what? If I say e of 7, what are you going to say? True or false? Again, e of 6, you will say true. So what is this? A relation of length 1, and we call that just a predicate because you are not related to anybody. You just have the property or you don't, and that's what we call predicate. But in this section, we'll mostly focus on binary relations. So those would be relations where we ask two objects to be related or not. Is that clear? So what then? So what is the definition of a relation? We're not going to say machine or something like that. Here is a very elegant, a little less intuitive, but very elegant definition. So, and by the way, elements do not need to be from the same set. So what is definition telling us? Let A and B be sets. What is a binary relation? It is a subset of A cross B. So definition. A binary relation R is a subset of A cross B. So how would that look like? Example? Let A be ABC. Let B be 1, 2. And let me define the relation like this. A1, B2. Is this a relation? First, does it match the definition? Because cross product are just pairs, and I assign some pairs. Actually, those are the pairs where I will answer true. So is A related to 1, yes or no? Yes. Is B related to 2? Yes. Is C related to 2? No, because it's not listed here. So whoever I listed, they give me true. Whoever is not listed gives me false. And that's an easiest way to kind of describe. So don't think always of relation to be that needs to be done formally or with the formula or with the words or explanation. It could be just, what is it, by the way? For example, a relation that SDG&E has between the SDG&E, that's gas and electric company, has between what? Between the households in San Diego and their bills for month of October, let's say. And then, so for every person is connected with certain, for example, number. So this is a relation between two types of objects. So that's how databases are very often organized. Actually, connections are established between certain objects, and they are not established between some other objects. So that's the only thing actually in the definition. So that's a subset where we specify who's related and who is not. All right, so I gave another example. Sometimes we define the relations without specifying the pairs of objects that are related, but using, for example, formula. So here's one example again. Example 6.1.2. We defined what? X, R, Y, if and only if x plus y equals 5. So look at the symbol that we are writing here. Are we writing equal or we are writing equivalent? Equivalent. Why? Because both sides have which value? True or false? And that's what we say, like in chapter 1, that they are equivalent. And by the way, we have to specify the domain. So it's the same set. Both A and B, they don't have to be the same. A and B, this time they are. So everything is on the same set. A, we can say equals B equals 1, 2, 3, 4. So do we understand the description of this relation? Yes or no? And then, For example, if we want to list the pairs that are related or not, very often what we do, we make a table, like a truth table. But this is the table a relation of a relation. So here's a relation, and we list everybody 1, 2, 3, 4, 1, 2, 3, 4. And then what do we do? On every cross, so well, we take first component on the left, second component on the right, and then on the place where they cross, we make the result true or false. So are 1 and 1 related? No, we put false here. 1 is only related with what? 4, the other 2 gets false. 2 is only related with 3, so it's true. Here are falses. 3 is related to 2, falses. And 4 is related to 1, true, false, false. Here it is. So from the description, we were able to list all the pairs, and actually, I didn't write the pairs, but I wrote the table of all the decisions for true and false. Can we write R as a set of ordered pairs, yes or no? Who's in there? Which pairs are in there? 1 and 4 is the first pair, 2 and 3, very good, and 4 and 1. Here it is. So this is, according to the definition, it's a subset of a product of set A with itself because it's relation on the set itself. So you see, there are alternative ways to describe a relation. Sometimes you use formula, sometimes you use table of true and false values, sometimes you list the pairs. They're all equally good. One more way how we very often represent relations, and that will probably particularly be important in chapter 7 when we start doing graphs, we actually represent relations using the arrows. So here is, we'll call it at this point, this is a diagram. So we do diagram of a relation. How do you form the diagram? So you enter all the elements from your domain, and then you put an arrow leading from one set to another. But arrow always goes from first component to second one. So for example, here, seeing this arrow L to D means who is related. Pair LD, not DL. So don't always assume that if they are related in one order, they are related in the other order. So not all the relations we say are symmetric. So L is related to D. Who else is related? D is related to C. D is related to B. B is related to A. What happens here? A and M go both ways. AM must be in the listing, but also it must be what? MA. So when you have a listing, you must list all connections in there. So that's another way to represent relations. What happened here? It's not that complicated. But what is it? Arrows are missing. When does that happen? Usually when we know, because of the property, that everything is symmetric, so that if everybody has double arrow, then we just don't write arrows at all. So when you see something like this, usually it means what? That arrows go what? Both ways. So like symmetric relation or undirected graph. All right, again, so this section is really designed to just help us to develop a feeling what relations are. Yes?
In that graph, is C related to B and D? I don't think so, right?
What's A?
It's only a straight line.
No, just straight lines connecting, that's it. So you cannot go transitively through it. It's not like trajectories. Although we'll comment about it in a minute, sometimes you want that to be done, but that's a different story. All right, so let's see another example of relations. So sometimes relations are described maybe in a combinatorial way, although this one's fairly simple, and it says the following. Let S be the set of all strings of A's and B's of length 4. How many strings are there, by the way? strings of A and B of length 4. 2 to the 4th, which is 16, yes. And now we define a relation. So how do we define relations? Two words or two strings are related if they both of them start and end with the same letter. Do we understand how that works? So, what can we do? Can we do 16 objects and then put the arrows? Or can we make a table with 16 objects? But generally, what might be the easiest way to describe what happens there? So let's see, 613. So words, how did we call them? S and T. SRT, S and T, begin and end with the same symbol. So what is the way to represent all this? Generally, what happens? There are clusters, in a way, of those strings. So who is in those clusters? So here is the cluster of the word that begin with A and end with A. Do you agree? Are they all related? So what do we do? Here is A, and then what? All four A's. A, B, A, B, A, and A, B, B, A. So these are all four words that begin and start with A. So what are we going to do? Although I didn't write them nicely, sorry. They shouldn't be in the line. It should be a little square. So A, B, A, B, A, and A, B, B, A. Are they all related, yes or no? So I can just connect them all without arrows and diagonal. Here is their part of the diagram. Are they related to anyone else? No, there is another cluster. What's the other cluster? AB cluster looks like this. I'm not going to write them all. There is BA cluster, looks the same. And then there is BB cluster, and looks the same. So this is how we can see this relation. Actually, there are a cluster of objects that are all interconnected, and then between those clusters, there's no communication at all. Do you agree? And this is very important, by the way, situation where actually you have partition of the whole domain into kind of those classes or those clusters of objects. But that is something that we'll study on Wednesday. So those special relations that have that clustering property. But as I said, from that description, this is the way to see the structure. Here is one very interesting relation. What is it? A divides B. What about this relation? Do you think that that one has arrows going both ways or not necessarily? So they don't go both ways. So how would you write a diagram for this one? So what are the numbers? 2, 3. But here it is. 2, 3, 4, 5, 6 are there. So here's a nice way to kind of organize this diagram. If someone's related, because there is a ranking between them, so 2 and 3, I put them next to each other. Why? Are they related or not? Is 2 factor of 3? No, 3 factor of 2, they are prime numbers, so they are unrelated for sure. What about 4? Related to so 2, so I'll put 4 above 2 and make an arrow going up there. And then what about 5? 5 is not related to anyone, it's a prime number. And then what about 6? 6 is somewhere on that second level, and then it will be related to both 2 and 3, and we'll have something like this. So you see, diagram here is very much different from the diagram that we saw a minute ago. A minute ago, we had complete clustering. Within cluster, everybody communicates, and outside of cluster, nobody communicates. And here we have, you see, 2 and 3 both communicate with 6. 2 goes to 4. It's never symmetric, never returned. Why? Because if A divides B and B divides A, and they are both positive, they must be the same number. But actually, I forgot something. I'm sorry. What did I forget? Is 2 related to itself? Yes or no? When that happens, we draw like little arrows around the number. So that shows that 2 is related to itself, because not all the relations have that property. So if it was greater, then it wouldn't be. So 5 is related to itself, 6 is related to itself, and 4 is also related to itself. This will be actually full diagram of this relation. All right, now if we know what relations are, then we can maybe understand better one definition that you saw many times in your calculus courses, and that's the definition of a function. Can someone recall that definition? So what is a function? That's what you studied. What do you study in pre-calculus? Functions. What about calculus 1? Functions. And calculus 2, again, functions. Calculus 3, functions. And DE, basically functions that solve differential equations. So what you study here are functions. So shouldn't we know precisely what functions are? So, what is a function?
Like a machine.
Oh, okay, that's a good intuition, but not a good definition. That's like, intuitive. That's a good picture. Yes, so function is like a machine where you do what? You have a place where you feed input and you get output. And input could be whatever you want, output can be whatever you want. And then if it's function of several variables, then you have a little more feeders. Agree? So that's a good picture. But that's not serious mathematical definition. What would you use? So every input has only one corresponding output. That's crucial thing about it. What's it?
At most one, right?
No. Every input has exactly one output, otherwise you are not input. If you are in the domain, you must have output. You wouldn't be in the domain then. So you must have exactly one output. Yes?
So it takes elements from one domain.
What is it? Is it like a shoe or animal, or give me a noun first and then talk about it, Whenever you are missing the word, you can always say neutrally, it is a mathematical object, and that's fine, But you must have a noun before you start going with properties. Yes?
It's just more generically, I guess.
Mm-hmm.
It's a way of solving a problem, like it models behavior or something.
Yes, you are telling us what their applications are, but you are not telling us what it is,
Wouldn't have to be a binary relation, would it?
Yes. No. So here it is. Since we are discussing, by the way, that's how they defined it in your algebra books or everywhere before here. So here it is. Here is a relation that's a little bit too dry, but very precise and good. So here it is. Definition. Let A and B be sets, and are subset of A cross B, which is what? Is that a relation, yes or no? Yes, subset of A cross B is a relation. Then what? R is a function if and only if for every x from A there exists one y from B such that x and y belong to R. here is a precise definition, ironclad.
Finally.
Yes, here it is, precise. And that's what we wanted when we learned predicate calculus and all that, that we can say things precisely and clearly. Then you can write a program that can check your definition and all those things. Your pictures are fine. Intuition is a beautiful thing. But you want to have also precise definitions that are checkable and explainable. And the only thing that's here that's a little missing, I said this, exists only one. We never formalized this in our course, or maybe I mentioned it a little bit. When you say there exists only one, what are you saying? There exists one and it's unique. So generally, if I want to say, no, this is not legal in our course, I'll write a little longer writing. It says what? For every x in A, there exists y in B, such that what? X and y belongs to R, and what else? For every z that wants the same, that z must be y. That's unique. So that stands for this only one. And for every z, x and z belong to R, implies z equals y. Here is that uniqueness.
For the uniqueness, that exclamation?
Yes. Sometimes it's this, sometimes it's exclamation mark. Absolutely right. Yeah, I forget. They are both used. Used interchangeably. And as I said, why do I like that it exists unique? Because this now looks really kind of hard to grasp and read and everything. But this actually stands for unique. So it has a property, and whoever else wants to have property must be equal to that y. So there's nobody else. So here's a precise definition of a function. Although I prefer the one that's less rigid. And that's for calculus course, that's how we define it very often. What is it? Usually I say the triple. So there are three objects. One is F, one is A, and one is B, where F is a subset of A. But they're the same one, basically. I just don't write this. And for every input, there's only one output. So usually people say that function is a triple. You need to specify what your domain is, what your range is, and what your rule is, and rule must have this uniqueness property. All right. So now we have a precise definition of a function. So generally what? If we have a relation, let me draw a relation. A, B, C. And then here are the outputs, 1, 2, and then if you draw arrows can never go back in that case. So is this a function? Yes. Why? Because actually what you are not allowed branching. The same A cannot have two images. You can have image sharing, but if you don't allow that, those functions are called what? One-to-one functions. So, but this is legitimate function. All right. Then we have enough language to discuss one combinatorial problem. And here it is. These are a couple of just problems to practice. Is a binary relation, is it a function or not? Is this binary relation a function? X equals y squared. So x and y are related if and only if x equals y squared. Is it a function or not? Is that music distracting you or what? So let me see. So we will say the following. X and y belongs to S if and only if x equals y squared. So this is the input. This is output. If I put x to be 9, do we have only one y corresponding here? So 9 is related to which number? Plus 3. Is it related to another number? Is this a function? No, it's not. You have a branching. Because if it was the other way around, y equals x squared, it would be okay. But 1x cannot have two. By the way, when you draw it, it's this parabola. So do we have vertical line test? Remember all that? Yes.
So it's also saying that the first.
First component, it's always easy input. Yes, yes. That's always the right. All right. What about this one? This one is wrong. However, you look at it, this is a circle. Do you agree? So circle does not, it is relation, because for every pair of points, I can tell you if they are on or not. So this is a binary relation, but it's not a function, because what you say, it doesn't meet vertical line test. That's how they call it in those more elementary courses. What would that be? Oh, by the way, but if you say it's not a function, how do you show that? On exam, I ask you this. Is this a function or not? Counterexample. Because every input should have only one output. You give me counterexample, give me one input with two outputs done, like I gave you here. 9 has two outputs, no more discussion. What about this one? Here's an interesting combinatorial question. Belongs maybe more into chapter 4. Suppose that A is a set of m elements and B is a set of n elements. If you want, we can do specific numbers. You want to do specific? Oh, let's do on the board specific numbers. Although it's the same, more or less. So A has 3 elements and B has 5. So 6, 1, 7. A has 3 elements, B has 5 elements. My question is, how many relations do we have between A and B?
From A to B, 5 to the power 3.
I'm not sure. Why 5 to the power 3? So question 1, how many relations? When you say 5 to the power of 3, what you did is, okay. No, functions are relations. This is much more. That's why this number is much bigger. How many relations?
Well, you not just multiply cardinalities together?
Why would you?
Oh, well, never mind.
One of the ways to record relation, we'll solve it in a second. I gave you alternative ways, and that shows you why it's important sometimes to have all these different ways to see object, because some of them, what's he?
5 to the power 3 m plus 3 to the power 5.
And, oh, you have or. No. Oh, but no, it could be who knows what. It could be that some of them have missing images. Some of them have double image. It could be all mess. Don't try functions at all. Remember, one of the ways, yes.
I think it's right that if a relation is just a subset of A cross B or B cross A, it would just be 3 times 5 times 2.
Oh, you said it nicely, then you messed it up. What did you say? What did you say? Relation is a subset of A cross B. Is that what you said? So A cross B has how many elements?
15.
And how many subsets do you have?
15 to the 15. Oh.
True. 2 to the 15. Don't you agree? Because what's a relation? Just a subset of A cross B. If A cross B has 15 elements, then you have 2 to the 15 subsets. So it is the same as cardinality of power set of A cross B. And that's it. Very nice. All right. But let's keep now discussion. Now, how many functions from A to B? Something very similar to what you said. What did you say? 3 to 5 or 5 to the 3? 5 to the power of 3. Well, very good. That's very good. Why? Because look at this. How many inputs do you have? How many inputs are there? 3. And possible outputs, 5. So here are those 3 inputs. 1, 2, 3. In how many ways can you fill in the output? You can put whatever you want. There are 5 possible values. Do you agree? Are they all good? Yes, you just don't take two values. So first one can have 5 different outputs. What about second one? 5. And third one? So if you want to combine, all possible versions, what do you get? Multiplication principle. So what's the answer? 5 to the third. Very good. 5 to the third functions. All right. Which fraction of the relations are functions? So when you write something arbitrarily or randomly, what's your chance to hit a function? So in this case, it would be what? 5 to the power 3 over 2 to the power of 15. So, not too big chance. Or, because, but in the general case, it would be what? N to the powers of n, 2 to the mn. So what would this be? If you take m out, 2 to the n over n raised to the m. So, or the other way around, 1 over. So that's how much more you have relations than functions. So if your n is small, you are okay. But if your n gets big, exponential is much stronger than this. And then when you raise that to m, so very soon, very tiny percentage of relations are functions. So relations are much richer than functions. What else? Let me see if there is more questions. Oh, there isn't. Maybe there is something in homework here. How many of these functions are one-to-one? Let me add 2 more questions. Question 4. How many functions? This might be an exam, or functions from A to B are one-to-one. So what does it mean one-to-one? It's the same as functions a minute ago. What is the image I can take for the first one? Can I take whatever I want? Yes or no?
Yes.
I can have 5 possible values. But then, next one's 4, because you cannot use the same one. You cannot repeat the values. And then what? 3. So that would be actually P and R. So 5 times 4 pi 3, which would be P5 3. How many of them are bijections? You know what are bijections? If it's 1 and 1 and on 2. So like for cardinality. So can I make what? If I have set A with 3 elements and B of 5, can I have a function? So here are 3 elements, A, B, C. And here are 5 numbers. Can I make function that's one-to-one and covers all the outputs? No, because there are too many of them, do you agree? But what if I had 5 and 5? So if I have 5 and 5, let me ask you now the same questions quickly, and that's where we'll finish. If I have 5 to 5, how many relations? 2 to the 25. How many are functions? 5 to the 5th. 3. How many of them are one-to-one? 5 factorial. But then what? If they are one-to-one, they also must be what? On 2, because if you have 5 inputs and they don't share outputs, do they need to cover all the outputs, yes or no? So that's 5 factorial. So generally that's what permutations are. They are bijections, actually form a set into itself. All right, so that's this fairly simple story about binary relations. And then we'll look now at their properties. So from this general introduction, we want to do a little more about their properties and some uses in cryptography. That will be interesting. Some parts of little beginnings of number theory And that should be interesting part of this section. What else? So today we cover section 6.1. You know we are now like half a class behind, so you have to go through the schedule now accordingly. So 6.1 is part of your homework. 6.2 we'll do on Wednesday. We'll try to catch up that other half, or otherwise I'll tell you on time if we need to postpone our exam 3. We'll talk about it. We'll see how we feel about all that, yeah.
So just the quiz from sections 1 and 2 and 5?
Quizzes from chapter 5.
Just, oh, the whole thing?
Oh, no, 5.1 and 5.2. You're absolutely right. 5.1 and 5.2.